So today we'll be learning about a new topic. So today we'll be learning about a new topic called So today we'll be learning about a new topic called Today we'll be learning about a new topic called as dimensions. So this is the part 2 of the previous video. So what are dimensions? So dimensions dimensions are defined as the this defined as the power raised to the base to the base physical quantity or base quantity, we can say. So power also means indices in this case. Power also means indices in this case. So this is the raised to the quantity. So we have to remember that dimensions is always raised to that particular quantity. Okay, let me write an example. Let me take example of mass. So when I write m power 1, that effectively means it is m. So when I write as m power 2, it means m into m, as it's m square. So moving on, let's write dimensional formula of some, or let's write dimensional formula of fundamental quantities. Dimensions of fundamental fundamental quantities. Okay, let's write the dimension of the first fundamental quantity, mass. It is m. So this is the base quantity which I'm representing. We can raise any power to the given base physical quantity. I can write this also as m power 100, means m into m into m into m into 100 times till 100. So length, so it is represented as L. Moving on to third one, time, T. Fourth one being temperature, temperature, temperature T. Fifth one being current, current. So it is A. Sixth one, luminous of intensity, CD, candela. And seventh one being amount of substance, amount of substance, which is MOL. We have to note that if we take that particular dimension of the 7 basic fundamental quantities, we can say that the dimensions are all are the first letters of the unit we wrote. For example, let me take current. For instance, we know it is ampere and the dimension is A. So what we can infer from here is that for fundamental quantities, the dimension is its its first letter of that unit. Okay, so moving on to the next topic called as dimensional formula. Okay, so what is a dimensional formula? So dimensional formula of an given physical quantity is the expression which represents how and which of the base quantities which are included in that quantity. So let me write that. So it is the formula of any 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 physical quantity, any physical quantity, and it is the expression it is the expression it is the expression which represents how and which of base quantity the base quantities are included in that given quantity. So so what I mean is that when I read the dimensional formula of mass, which is m power 1, L power 0, T power 0, I have included three base physical quantities, and there is power raised to the given quantity, which is mass. The given quantity, which is mass, there is power raised to mass. So when we write dimensional formula for that given quantity, we always raise the power. Uh, we always raise the power the quantities which is expressed in that definition. For example, for instance, let me take an example in the next page. Kinetic energy, Ke. We know it is half into m into v square. So half into m into v squares. So we know that dimensional formula of mass is 1, and velocity so velocity, its dimensional formula is L power 1 and T power minus 1. We'll learn the dimensional formula of all the quantities in a few moments. And it is whole square. So let's multiply 2 as per the formula that says a power n whole power m is equals to a power n into m. So if you apply the same analogy out here, that would become L power 2 and T power minus 2. So, and moreover, half is dimensionless. We learn about all the rules which are associated to that. So dimensional formula of kinetic energy is written as m power 1 L power 2 T power minus 2. So the definition in the previous slide says that when we say kinetic energy and the definition or the formula which is there here, we have raised the power to those quantities which are involved with the formula or the definition. Okay, moving on. Moving on. So let's take the definition of what is a dimensional equation. What is dimensional equation? Okay, so it is defined as the equation. It is the equation which is obtained, which is obtained, is obtained by equating a physical quantity, equating a physical quantity with its dimensional formula, with its dimensional formula. So this is the definition of dimensional equation. What what does this exactly mean? Okay, let's deep dive into that. So dimensional equation. So it is nothing but an equation. We know equation, for example, x plus y is equals to 1. So this is this kind of an any equation. So we can assume it as an any equation obtained, which is obtained. Like we get that when we equate powers or indices to the physical quantity. In the previous slide, I have uh, wrote the dimensional formula or the dimensional equation precisely for kinetic energy, as we can see here, as we have converted it from its original formula of kinetic energy. So moving on to rules governing, rules governing, rules governing. So any constant, so the first rule says that any constant, for example, like pi, uh, 1 by 2 root 3, etc., etc., are dimensionless. So that's the reason in the dimensional formula of kinetic energy, even though the equation at half, I have to consider it as 0 because a constant is dimensionless according to the rules which are governing it. Okay. Second of all, we have to obey the rules of algebra to the physical quantities. What I mean is, for example, I have a dimensional formula like m power 2 L power 3 T power minus 2, for example, and I have L power minus 2 T power 2. So if I have to simplify to write the complete dimensional formula, I have to shift it to the numerator. So it converts to m power 2 L power 3 plus 2. If I shift the negative, it turns into positive. If I shift the positive, it turns into negative. So what the definition meant was, we have to follow the normal rules of mathematics. So It's nothing but normal rules of maths are applied or are to be followed or to be followed. So let's continue. So if minus 2 goes up, it becomes plus 2, and t power minus 2, and it was plus 2, so it should become minus 2. So and we solve this, we'll get m power 2, uh, l power 5, t power minus 4. And moreover, we have to also note that we have to equate to the same quantities. I mean that I cannot apply this to m or t. I have to only apply this to L. So we have to only do the calculation to the same quantity, which is L or T in this case. Moving on, uh, let's write dimensions of some given quantities or some basic quantities. Let's start with all the 7 fundamental quantities. Let's try to all the 7 fundamental quantities. Dimensions of all the fundamental quantities. So beginning with mass, it is nothing but m power 0, sorry, it's m power 1, l power 0, t power 0. So so and so the other rule out here is we have to we have to represent usually with base physical quantities, which are mass, length, and time. From the part 1 video, we know that mass, length, and time are the base physical quantities. So usually we write a dimensional formula for mass, length, and time, and we raise the power to those. Like if any other quantities are not involved, so we usually write mass, length, and time, and we raise the powers accordingly. So it was only mass, so we raise m power 1, and the rest l and t, which are not in the formula, so we write 0, as anything to the power 0 is dimensionless in this case, as per the law which is governing the dimensions. So moving on to length. Uh, if you have guessed it's right, it is m power 0, l power 1, and it's t power 0. Moving out to the third one, which is time, which is m power 0, l power 0, t power 1. Moving on to the fourth one, which is temperature. In the beginning of the session, we had written some of the uh, dimensions of fundamental quantities. So these fundamental quantities, we raise the power to them, and we write dimensional formula of derived quantities using all of this. So the fundamental quantities have their own dimensional formula, but as per we know, dimensional quantities of derived quantities should be derived using the dimensional formula of fundamental quantities, as derived units depend on fundamental quantities for their existence as per the definition of derived units. So moving on to temperature, which is m power 0, l power 0, t power 0, k power 1. We know it's Kelvin, so it's K, so it's K power 1. Fifth one, current. Current, so it is m power 0, l power 0, t power 0, a power 1. Uh, moving on to luminous luminous of intensity, luminous of intensity, which is m power 0, l power 0, t power 0, cd to the power 1, and amount of substance, which is m power 0, l power 0, t power 0, m mole power 1. Okay, let's write dimensions of derived units now. So let me change the pen color so we can differentiate. Okay, dimensions of dimensions of derived units. Okay, let's start with the most basic derived unit, which is area. So area is, we know, as we know, it is length into length, so it is L square. Moving out to the second one, which is density. As the formula of density is mass per volume. Let's write the dimensional formula of volume first. Let's stick it as third. We know volume is length into length into length, which is length cube. So the dimensional formula of density becomes m power 1 by L power 3, which converts to m power 1 L power minus 3 as I'm shifting it up. As we know, positive turns into negative, negative turns into positive. Okay, moving out to fourth one, which is force. Uh, so let me write it directly, which is m power 1 L power 1 t power minus 2. Okay. Moving out to fifth one, which is surface tension. Uh, the formula of surface tension is force force by length, force by length. So as you know, the dimensional formula of force, that is m power 1 L power 1 t power 2 and length being L, so L power 1. So when I shift that up, which becomes m power 1 L power 0. Why? Because it is L power 1 minus 1, so that becomes 0, and t power minus 2, t power minus 2. Okay. Moving on to momentum. I'm not writing the formulas of force and other quantities. Why? Because those have to be taught in detail. So it's better that I don't write the formulas now, because that will cause a confusion while understanding the topics further. Okay. Moving on to sixth one, momentum. Which is m power 1 L power 1 t power 1. Seventh one, pressure. Pressure being force per unit area or area. As we know, the formula of force is m power 1 L power 1 t power minus 2 by area L square. So we know it goes up, it turns into negative, plus 1 minus 2, that becomes minus 1. So it is m power 1 L power minus 1 and t power 2. Okay, continuing to the eighth one, which is wavelength. uh, Wavelength is nothing but when we take so uh, so when we take so okay, so yeah, So assuming this as a wave, and let me draw a transverse wave. So if it is a wave, so the distance between the uh, two two uh, two crust and two troughs is called wavelength. So it's nothing but length. So it nothing means it means length. So the dimensional formula of wavelength is L power 1. Okay. Moving out to ninth one. Moving out to the ninth one. Angle. Angle, it is dimensionless. It's a dimensionless quantity. Uh, the reason being, okay, yeah. When we say an angle, it it is dimensionless. Why? Because it's a ratio and everything cancels. So it is dimensionless, and there are many dimensionless quantities. For example, there's a dimensionless quantity called strain, which comes in the properties of solids, in the chapter properties of solids. And there is refractive index, which was in class 9 and 10. So it's a ratio as well. So everything is a ratio, but everything cancels out here. Everything cancels out here. So it is dimensionless. So I cannot just say the formula now, and as I said, it might confuse. So it's better that I don't say the formula. uh, you guys just uh, know that strain, refractive index, angle are some examples of dimensionless quantity. Moving out to kinetic energy, which is 11th one. Kinetic energy. We know the formula of kinetic energy is half into m into v square, half mv square. So as we know from the previous slides, that half is 0. So m is m power 1, v is L power 1, t power minus 1, and its whole square. So it is m power 1, L power 2, t power minus 2. So moving out to potential energy, which is mgh. Mass, m power 1. Gravity, which is m power minus 1, uh, L power 3, t power minus 2 into h. uh, the formula of gravity, we'll learn it in the chapter gravitation, so no worries on that. Now let's calculate the dimensional formula of this, which again turns out to be m power 1, L power 2, t power minus 2. We have to keep in mind that every form of energy, irrespective of their formula, the dimensional formula is same nevertheless. It is same. It might be any form of energy. It might be it might be mechanical energy, it might be heat energy, it might be electrical energy, it might be nuclear energy, but the dimensional formula of all of those remains m power 1, L power 2, t power minus 2, irrespective of any kind of energy it is. So we can say that it might be any kind of energy, it might be any kind of length, it might be any kind of area, it might be any kind of pressure. Irrespective, if it has the same meaning, the dimensional formula remains same nevertheless. Okay. Moving out to uh, one more. Let's go to some constants now. Which let's go to 14th one. It's 13th one. Planck constant. It is one of the most used constant in the chapter atomic structure in grade 11 as well. Uh, this nothing but this nothing but means Planck's constant. As we know that Mr. Planck proposed a theory called black body radiation, etc., etc., uh, where he gave the formula that E is equals to h nu. So the formula, we write the dimensional formula for this. So here h is called Planck's constant. It is called as Planck's constant. So we write dimensional formula for this. So h, we write dimensional formula for h. So the dimensional formula for h is m power 1 L power 2 T power minus 1. Why? Because it's energy into frequency, which is length, so it converts to m power 1 L power 2 T power minus 1. So uh, moving out to one complex, it might sound complex, but if you guys have uh, given concentration to the rules which I said before, this might be easy. 6 pi 1 by 2 uh, uh, root 2 into uh, into V. Okay, let's write dimensional formula for this. We know it is dimensionless, it is dimensionless, it is dimensionless. So the only thing which remains is velocity, which is L power 1 T power minus 1. Yeah. So this were some basic basic dimensional formulas. So let's learn a new topic called principle of homogeneity. Principle of homogeneity. Principle of homogeneity. Principle of homogeneity. Yeah. So, uh, so what does this principle says? So, in a given, if in a given relation, if in a given relation, terms on both sides, both sides have same dimensional or dimensions, then then the relation the relation is dimensionally correct. So what does that mean? So if the dimension of RHS is equals to dimension of LHS, so we say the quantities to be dimensionally correct. Dimensionally correct. So moving on, according to this principle, according to this according to this principle, only only same physical only same physical only same physical quantities can be added or be subtracted. So we can perform the arithmetic operation of addition subtraction to the to the given same physical quantity. So what I mean is that if there is m l t and there is m l t, I can perform addition and subtraction to only m. Like I can perform addition and subtraction of this m to this m, and this l to this l, and this t to this t. I cannot just perform addition and subtraction to from t to m or t to l. I have to perform addition and subtraction to that physical quantity only. Okay. uh, we have to note an important point, that let me read it as note. We have to note that uh, okay, okay, uh, we have to note that to note that for an equation for an equation to be correct, the dimension to the dimension the dimensions of LHS must be same to dimensions of RHS. Should be same to direction of dimensions of RHS. That's the same rule I wrote before, that dimensions of LHS should be equal to dimensions of RHS. But it's an important note that we can make a notable mistake out here if we don't see to this rule. And okay, let's solve a question on this. So let's prove that F is equals to MVR. So this is a random formula for now. Let's see if if this is dimensionally correct. So as we know that F is equals to m power 1 L power 1 t power minus 2, and MVR m into v square into divided by r, which is nothing but m into L power 2 t power minus 2 by L power 1. This becomes L power 1, which is equals to m power 1 L power 1 t power minus 2. So as LHS is equals to RHS now, as LHS is equals to RHS, so this is dimensionally correct. This is dimensionally correct. So let's do another example. Uh, so let's see that whether this equation that p is equals to root of 2mk is dimensionally correct or not. So p nothing but is equal to momentum. P is equals to momentum. So let's go back to the previous slides to see the dimensional formula of momentum, which is m power 1 L power 1 t power minus 1. So dimension of momentum is m power 1 L power 1 t power minus 1 and root of 2mk. We know that 2 is dimensionless, and okay, as we know, root of 2mk can be written as 2 into m into k whole power 1 by 2. I can write the root as whole power 1 by 2. So because this is dimensionless, m power 1 by 2, k power 1 by 2. So uh, k can be also, I can write that as m power 1 by 2. So this is that, and get K as m power 1, L power 2, T power minus 2, as that's an kinetic energy. K means kinetic energy out here. So O power 1 by 2. So that 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 whole simplifies into 2. 2 is cancelled. So m square L square T power minus 2. As the bases are equal, I can do the operation between this and this. So so it turns out to be the uh, m power 2 t power 2 t power minus 2, which turns out to be m power 1 L power 1 t power minus 1. So it is dimensionally correct. So LHS is equals to RHS. So this formula is correct. Both the formula is also correct and the dimensional formulas are also correct. I can say that. I have performed basic arithmetic operations that if the powers are equal, I can equate the bases. I can equate the bases. So I've used that property to simplify the question here. So let's move on to application. Application of dimensional formula. So what are the applications? So the first application notably is we can find the relation uh, between the unknown physical physical quantities. Unknown physical quantities. Okay, let's take an example and look at this. Okay, as we know, kinetic energy of a body depends on mass and speed of the body. We need to find a relation. So we need to find a relation between between these physical quantities. So Ke is directly proportional to m power a, which is mass. So Ke I can write it as lambda into m power a into v power b, as it's also depends on velocity. So this is dimensionless quantity. So this is 0. So Ke so let me write the relation of v also. It is also directly proportional to v power b. So I can write that this is the relations. So this is the actual problem solving. Okay. So this is the relation. K is equals to lambda. I've introduced a constant to remove the proportionality. As we know, to remove the proportionality, we need to introduce a constant. Have took the constant as lambda. As per rules governing dimensional analysis, lambda is equals to 0. So it's Ke is equals to m power a v power b. So we know dimensional formula of Ke is m power 1 L power 2 d power minus 2 is equals to m of a velocity. So I can write velocity as L power 1 and t power minus 1 whole power b. So this simplifies into m power 1 L power 2 t power minus 2. So here I was not knowing the relation of mass. So I got m power a and L power b and t power minus b. I don't know any relation. So from here I can directly say that a is equals to 1, L is equals to 2, and b is equals to 2, and c is equals to minus 2. I can directly, like write the dimensional formula. If I just don't know, I can use dimensional analysis to the dimensional formula. Okay, moving on. Uh, Moving on to the other application. The previous application was we can find the relation between unknown physical quantities. The other relation is uh, we can convert from uh, one unit, one system of unit to other other system of unit. I can convert from one given unit to the other given unit. Like I can convert a kg into grams, grams back to kg, something like that. We can convert units back to their original, to the original. I can convert them back and forth. So we go to the last major application. We can check the dimensional correctness dimensional correctness of the equation from the previous examples. Let me go back to some previous examples. Yeah, so we had f is equals to mv square by r. So f is equals to mv square by r. I was not knowing that if f is truly equal to mv square by r. If we, as we solved that, we got to know that LHS is equals to RHS. So I can confidently say that that force is also equal to mv square by r. So this brings out a relation between the LHS and RHS, and we have to note that in some cases, LHS LHS might not be equal to RHS. In the further coming chapters, as we write the dimensional formulas for the for the formulas in that chapter, we'll just come to know. In some cases, LHS is not equal to RHS, but this is only 1 to 2% in the entire formula of physics which comes under this. In 98 to 99% of the cases, it's always equal to LHS is equals to RHS. But we have to be careful, and we have to check for this. Why? Because in some exams, they can give LHS is not equal to RHS, and we might lose our marks. Okay. So I just forgot to add one point here. So the formula to convert from one quantity to other quantity is m by m power a into a, or or I just erase this. So let me erase this. Okay, no problem. The formula is m by m, that is small m to the capital M power a. So for example, if I have in kg, basically I write the SI units out here. SI units out here. So it's m power a, L by L power b, and T by T power c. T power c. So it's okay. Let me write it in the next page. So the formula is m by m into whole power a, L by L whole power b, T by T whole power c, and etc. For all the fundamental quantities, we can just do that. So it is the end of the chapter of physical quantities, units, and dimensions. So in the upcoming videos, as per the NCRT, the next is kinematics. So the next video will be on kinematics. So hope you guys subscribe to the channel, and like the video and drop down the comments on what to improve, etc. And we'll meet soonly on the topic called kinematics.